Thank you very much, everyone. Okay, today I will be presenting my recent research work on CMOS digital to analog converter design, where we are targeting for 1 giga sample per second application for 5G new radio protocols, basically. So, we are moving to gigabit per second wireless communication era, 5G new radio, 5G, and probably terahertz in the future, where currently active research is going on. So what we need here is basically, what we have here is huge data bandwidth. Okay, so we are operating in a world that have very high data rate. We want everything to be fast, to be processed fast, and we have very high data rate. But how are we going to send it over the air to work part of the wireless communication system, especially for high-end mobile phone application and mobile wireless communication? So we need to have a bridge, a strong bridge, a conversion mechanism to convert this huge data bandwidth to analog domain. And currently, we are dealing with 3 main protocols for wireless communication, 16, 64, 256 QAM, developed by mobile chip designers, basically Qualcomm. Qualcomm is moving forward, currently actively working in 256 QAM and 64 QAMs, basically. So these are the challenges that mobile wireless communication designers are facing at the moment. So what is the issue here right now is when you are trying to convert a digital signal to an analog domain, there are 3 issues mostly the designers will face. Number 1 is quantization noise, which is the in-band noise. The second one is out-of-band noise limits. The third one is we are dealing with a signal which have non-constant amplitude, okay, which is subject to peak to average power ratio. And it's difficult for the digital signals to be modeled accordingly to meet the analog demand, where you need to give a clean analog signal to the transmitter, basically, for you to amplify it successfully, and the receiver receive the signals successfully as well. So when we are dealing with 5G new radio, protocol level by the 3GPP communication system, basically, this protocol is important because it has high throughput, reliability, flexibility, and low latency. And for cellular, basically, we are dealing a bandwidth of baseband bandwidth up to 500 megahertz before you convert it to RF frequencies, basically, and the clock speeds typically is about 2,800 megahertz for a 16-bit system. So key requirement, therefore the key requirement for 5G new radio DAC is you need to have about 70 dB of spurious-free dynamic range. So noise is an important factor, followed by the low power consumption and linearity, because you are converting digital signal back to analog. So linearity is a constant. It's a constant requirement, consistent requirement, and also you need to ensure that there are no glitches, basically. Right? How do we characterize that we have designed a good digital to analog converter? So researchers always compete and consistently try to come up with a figure of merit, okay, which is an equation which relates to the power consumption, the noise, and also the sampling rate, basically. This is the typical figure of merit for DAC design. And some of the DAC architectures that have been published recently ensures that using very unique level of biasing circuits to solve all these noise issue, basically. It's a trade-off between noise and power consumption. Because we are dealing with a very high data rate system, so power consumption is something that we really have to look into. 3 things: balance performance between power consumption, noise, and also linearity. Okay. Now, these are some of the simple, basic current. We are revisiting the fundamental options that we have, which is one of the fundamental circuits that we have is basically current steering. So researchers are revisiting back current steerings, switching units, unary unit, binary unit, in order for them to have a balanced performance to meet the figure of merit numbers, basically. And these are some of example of hybrid DAC, where you have current steering and also binary weighted resistors. This is some fundamentals requirements, fundamental circuits, basically. Now, in our work, this is our design methodology. So what we are trying to do here to come up with a balanced design in terms of power consumption, noise, and linearity, as I mentioned. So what we are proposing a solution known as the hybrid DAC, where we are trying to divide it in two main distinct sections, which is known as the thermometer coding, involving decoders and filters, followed by some current source cells, and also binary weighted resistor covering the other half. So this is for a 16-bit design, basically. So it's a differential, and then we have all this positive and negative voltage, and then we will try to supply into the reconstruction filter to regenerate back the analog signal to be supplied to the transmitters, basically, the radio frequency transmitters, which is operating typically about 5 gigahertz. So this is the detailed schematic of our work, basically, where we have about 10 bits of LSB, and then these are the MSB segments. So the design strategy that we used here, I would like to share with you. First, bit partitioning, 16 bits, we partition to 10 to 6. Okay, 10 will be using thermometer coding, because thermometer coding is known for its high linearity, but it has very high power consumption as well, followed by the binary weighted resistors is low linearity, and because it involves the passive components, so the power consumption is low. So you got to balance up. The rationing is quite important here, followed by the current source design. It's very important for us to have a good current source design, followed by binary weighted resistive ladder, and then we did the decoder, followed by a glitch filter, and then reconstruction and a full chip layout, basically. So this is the starting point, the bit partitioning and the current source design, basically. So this is how we did the partitioning from the LSB section, and these are the MSB sections. So it's just ensure that for the current source, that all the transistors are operating in saturation region. It's very important for us to ensure that the DC follows all the GM laws and also the saturation drain current equations as well, including the channel length modulation. Now, the principle of operation of the current source cell, as shown here, basically, so we have ensure all these transistors are in saturation and fulfill all these equations to make sure that the drain saturation current is the overdrive voltage is always more than the VDS saturation. So we were using CMOS 65 nanometer TSMC process to do this design. So it has a pretty good number of VTH. I think it's about 0.43 volt or 0.3, yeah, 0.3 volt or less than that. So it's quite helpful for us to meet all the saturation conditions easily in 65 nanometer as compared to we used to work in 180 nanometer and ST Micro 65, but we found out that it's quite robust using this particular process, basically. And then we did a huge number of simulations, especially PVTs. Basically, this is the PVT plots across VDDs, output current, and also the temperature, pretty good numbers. And then linearity, we got to take care. Linearity basically is contributed by the current source, so we got to take care of the output impedance. Make sure the lower the output impedance, you will suffer in terms of linearity. But higher output impedance, you have a good linearity, but you have bad power consumption. So you have to come up with a mechanism on that. So when we try to balance this one, because our main goal is to reduce the power consumption while maintaining the fundamental requirement of this linearity and also the noise. So followed by this binary weighted resistors design. So we tested out theoretical and simulated schematic simulations is quite accurate. So that's the beauty of using this process technology. We'll enjoy it. Whatever we calculated it, we simulated it, we got it. So the model accuracy was fantastic, basically. And then we move on to design the decoder, 6 to 3 decoder. This is the thermometer decoding that we have designed for the 6 bits, MS bits, basically. And what we found out is when we try to design a chip for low power consumption, you suffer a lot of glitches. Almost every single time microseconds you're running across is full of glitches, basically. So I think this is probably because the impedance of the current source is too low. We are trying to drive it at minimum requirement of the saturation current, so we are having this problem. So to solve it, basically, we introduce a deglitch filter in our design. Okay, so this helps us to solve the issues. And then we integrated the total solution, basically, and then these are the equations that fulfill all these simulation numbers that we have on the both differential output, V positive and V negative. And then we feed into the reconstruction filter because we want to have a sinusoidal signal to be fixed, to be supplied to the mixer of the transmitter, which is running at 5 gigahertz. So we are trying to develop about 490 megahertz kind of a signal, which will be up-converted later to 5 gigahertz before it being transmitted. And this is basically the chip layout that we have, and followed by the, this is the fabricated chip. We use TSMC 65 nanometer, as I mentioned. It's less than 1 mm squared, 0.95 times 0.40. And the layout was done meticulously because we are very concerned on the resistive loss contributed by this layout. So we cannot afford to lose any level of voltage. So we are trying even our groundings. So this is the technique, grounding techniques that we use. We partition the grounding, we split the groundings to ensure that you enjoy a close post-layout simulation result as compared to schematic. So this is the layout of the 6 to 63 decoder. So every single block, we try to test the post layout because we want to make sure that we don't lose the pattern. So we don't develop the entire chip, and then you check the DRC and LVS. That's not it's very time consuming. It's very difficult for you to detect the errors. So we do block by block. So it's easier for us to detect if there's any errors and solve it immediately. So that's why we are sharing this. So this is the decoder, and this followed by the current source cells. Okay, pretty good numbers. Theoretical is about 40 micron, and then post layout we got about 39.92, which is close to 40 micron. Percentage of error is about 0.2%. And these are the layout of the 126 current source cells, basically. Followed by the binary weighted resistive ladder. So this is the layout of the binary weighted resistive ladder, about 220 micron times 33. And then this is even we split the DAC to a DAC positive and DAC negative. So for us to do the post-layout simulations effectively, basically. And this is the RC reconstruction filter inside the DAC. So this is the filter that we designed. And followed by our measurement setup, we fabricated it. Took us about 2.5 months for us to get back the chip, 2.5 to 3 months. And then this is a setup for us to measure the DAC. We did 2 types. First, we do an on-chip wafer probing on the left-hand side. And then on the right-hand side, we also did a wire bond, basically. So the top one is a DAC, the below one is an ADC. So we taped out together the digital analog converter and also the ADC, basically. So measurement result shows that power consumption of the DAC mainly still current source cells, about 60.29%, followed by the filters and binary weighted resistors, decoders, and finally is the reconstruction filters. So these are the measured output voltage that we obtained. And this is the measured DNL, INL. You cannot straightforward measure DNL, INL, so we have to put it back into MATLAB and plot the graphs. So this is what we obtained. So it's a pretty good number as well, the DNL and the INL numbers. Followed by the SNR and SFDR. SNR and SFDR is 80 dB, measured close to DC 1 point, and also at the what do you call the intermediate frequency for the wireless communication, which is about 490 megahertz, which is more than Nike's rate. So we measure at two conditions. One is close to DC 50 megahertz, and then and at more than Nike's rate. So this is the reconstructed filter measured at 490 gigahertz, and we also tested the FOM for 20 samples. So that is the mean value and the standard deviation that we obtained for 20 such chips. And then this is the final performance summary that we have, which is about 16-bit, and active area is about 0.06 mm squared with an FOM of 5.506 and 13.83 at 490 megahertz for resolution 16-bit. And we compared our work with some recent published work from 65 up to 55 as well. So the FOM is one of the lowest basically we scored as set for reference number 2, but reference number 2 is a post-layout simulation result. Power consumption that we achieve is about 45 milliwatt with a speed for 1000 megasample per second up to bandwidth 490 megahertz. Okay. And then this is the transceiver that we developed, chip number 1 on the left-hand side. Okay, so the goal of the project is to develop the entire thing as one single chip solution. That means you have the receiver, transmitter, followed by the ADC and also the DAC. But because we are quite skeptical on the performance of the DAC, ADC once it combined with the high frequency transceiver, what we did is we divide the chip into 2, and then we try to do a wire bonding solution measured on the PCB to see whether we are meeting the functionality, especially when you're dealing with transmitter. A receiver, you will be dealing with noise figure, and transmitter also you have to deal with the linearity of the transmitter itself. So the way that we did it is split it 2 and then try to do PCB tuning to achieve the performance that we desired, and then later part for us to combine them as one single chip solution. That means from analog right up to mixed signal over here. And then the measurement result was quite successful. So right now, currently, we are focusing on developing this as a full chip. We are doing 2 processes right now. One is in 65, another one is in 28 TSMC as well. Okay, the conclusion is we have achieved 16 bits, CMOS 65 nanometer, which is achieving a DNL of 0.27, 2.25, SFDR 72 and 70, and operating at 1 gigasample per second, power consumption of 45 milliwatt. The future work is extension to higher data rates and advanced power management techniques. Basically, we're going to introduce regulators, because this is the base body of the chip, so the impact of the regulators is not being calculated. We use thin oxide transistors, 1.2 volt, but eventually you end up with thick oxide transistors because you're dealing with outside battery world, which is about 4 volts, so need about 2.5 volt to 3.3 volts, so we are not using that again. And also the transmitter part, the power amplifier is using thick oxide transistors, so it's going to be a kind of a complicated recipe that we have to deal with. And then process node scaling on-chip calibration, AI-driven optimization, and noise reduction strategies. So for entire wireless communication system that we have right now in our mobile is chip 1 is being done in non-CMOS process, which is gallium arsenide, because gallium arsenides give you exceptional low noise figure and high output power, and reliability is quite good in supporting high output power. So research is still focusing, research is trying to move chip 1 to CMOS because we want to have all CMOS solution right now. So the problem that we have is the fundamental performance is there, but reliability is still an issue, and noise figure is still an issue to achieve that. So that's why lowering down the gate to 28 probably may help us in lowering down the noise figure, but you may suffer in delivering the desired output power of the wireless communication transceiver chip. But once we achieve that, then it will be a great achievement for the IC design community, basically. And then we need to have an on-chip calibration to solve these offset voltage issues that you will face, provided by AI-driven optimization, because we took this to 2 years to develop the entire system. So if we want to cut, our current research is we want to cut short the design time, basically using AI-driven optimization. So we plan to work on optimizing how the model can be optimized automatically so that we can reduce the design cycle time, and also the noise reduction strategies basically is ongoing. So we published our work. This is a collaboration with University of Cambridge. So we published our work together with them, and it was recently accepted. Thank you very much.
Okay, thank you very much for Dr.
Jaga.
Yeah. Thank you, Dr. Jaga's excellent talk. Thank you very much.
Thank you.
So, any question from the audience? Any question? Maybe we can have one question, one or two questions. Any question?
Is the voltage drop across the current source as a transistor which act like a current source a problem in terms of linearity, and how do you solve this challenge that you don't have channel length modulation on the transistors which affect the linearity if the current changes, you know?
Okay. If you take a look from fundamental point of view, okay, if the channel length of the transistor is more than 0.5 micron or close to 1 micron, the transistor will not be suffering in terms of channel length modulation. So the IV curve will be pretty flat. Now, when you reduce the channel length, okay, to 180, 65 basically, and then you can see the curve is going upwards towards trend, and then you start suffering channel length modulation. So, but the question that we need to ask is, can we live with a channel length of 0.5 micron as a quick solution? Right, 0.5 micron above, because 65 nanometer, if you use for analog design, 65 nanometer exactly gate length, you are not able to solve the channel length modulation. You got to live with it, right? But the advantage using 65 nanometer right now is for that particular device size, you have enormous current, because for the density level that you have enormous drain current as compared to 1 micron. So what we did here is basically we try to design the chip with the transistor with 65 nanometers in order for us to have smaller area. At the same time, at that particular density, we have more current, but we suffered in terms of, you start suffering in terms of power consumption and the glitching mechanism. So that's why we are coming with the deglitch filters to solve that issue. Another way to look into it is you need to make sure that the impedance of the current source Z out is high enough. If it is high enough with the basic simulations, so probably you will try to reduce the channel length modulation effect, but you got to live with it. And how that will be very impactful to you. If I use an ideal transistor, my DNL, INL is going to be pretty good. But that's a trade-off that I have currently right now, basically. So for analog design, for digital design, yes, it is a matter for you to reduce 65, 28, 14, 16. But for analog channel length, you have to study carefully whether how bad is going to be your channel length modulation effect going to be. So that's why we may want to increase the length of the transistor just to solve that issue. Basically, it's a trade-off game, basically.
Okay, thank you very much. So, any other question from the audience? Maybe we can have one more question.
Okay, great talk. I have one brief question. We have see the resistance tree and controlled by some switch. So I would like to know how to overcome the mismatch, because the mismatch will improve the INL and the DNL. So how do you to decide the resistance tree and consider the resistance of the switch, because they will induce some mismatch in the street. Okay.
Okay. So for the mismatch, basically, the way that we did it is, when you talk about mismatch, basically, the mismatch is coming from the current source and the switch, basically. So as I mentioned just now, do we really pay attention to the output impedance of the current source? Okay, so the switch is a basic switch. As long as the transistors are in saturation, or for current source is good enough, and for switch, as long as it is operating in triode linear, as long as the switching mechanisms work, then it's good enough. But do we really pay attention on the output impedance? So that defines the W over L size of the transistor that you need, basically. So mismatch means mismatch between the impedance of one block to another block. So that's what we call mismatch. And basically that mismatch is fundamental, is your voltage and your current, which we can categorize them as impedance to make our life easier. So when we solve it in schematic level, you'll have another mismatch issue when you do layout, basically. When your resistance value have 5% tolerance, for example, right? So you're going to suffer another mismatch, basically. So what we did is, ideally, when you design a chip, basically, the performance is really matter. The performance need to be met. INL, DNL has to be met, else you cannot sell the chip. You cannot call it as a DAC anymore. But your skill set is to design the chip while meeting the specification with low power consumption, because that's what the world wants right now. I want a low power consumption solution for everybody, so that I can use my battery as long as I want, right? So when people trying to focus in the game to reduce the power consumption, because the chip with the lower power consumption with reasonable performance is the chip that's going to win the game. When you talk about research, business, whatever it is, right? People are going to buy the chip with low power consumption. But when you reduce the low power consumption, you will try to start to trade off in the fundamental performance. So we have to really take care on it in a balanced term of things, so that it's all pretty much balanced. So do not start the design when someone told the spec with you, I want low power consumption. Don't start the design with low power consumption first. It's a bad idea. It's a bad start. Make sure the chip meet the fundamental performance first, so that it can be categorized or qualified, whether it's an amplifier, it's a DAC, ADC, whatever so. Then the second generation has to be on the power consumptions, basically. So let's not try to confuse. So when we focus on this, Professor, what happens is we have all this issue coming back, mismatch. Okay, mismatch to the layout. What we did that, yeah, we have some mismatch, and that mismatch causes glitches. Right? Fundamentally, glitches is a digital problem, right? But we are trying to see that when the digital glitches, we try to convert it to analog frequency, the baseband frequency runs away. Right? So we do not know actually where is the problem comes. If you do a system level design, system level simulation, and all the stuff, basically. So the glitches of the bit that introduced by the bits will be translated to the analog world, and we will feed into the mixers, power amplifier, and transmit to the air, and then we're going to get the wrong data end of the day. So that's how we did. So we solve it with the de-glitch filter mechanism, Professor. Thank you.